Hi, I'm Benjamin Kroll, and in this video I'm going to show you how to get started on a lab where you're going to measure the field of this little disk magnet as a function of the distance from the magnet. This video is not supposed to be a substitute for actually doing the lab and taking your own data. I won't actually record the data in the video. It's really meant just to help you understand how the whole thing works. We're using this during the COVID-19 epidemic, where I won't be there at your house to look over your shoulder while you use these materials that we've mailed to you so you can do this experiment at home. So the idea here is for you to see what it looks like so that you are not confused about how to get started. Here's where the information about the lab is. It's in this book, which is free online as a PDF file. And the title of the lab says bar magnet, but we're actually using a disk magnet because that was what we were able to get for 50 cents a piece on Amazon. The reason the lab is labeled lab number 1 is because it's for students who are just starting out in their study of electricity and magnetism. So you really don't need to have a lot of prior knowledge about electric or magnetic fields here. For our purposes here, all you really need to know is that these things exist in space and they're vectors. So when you have two different sources of a field acting together, those two fields add like vectors to create the total field that we would observe at that point in space. It's actually a little unusual that I teach magnetism side by side with electricity from the very first week of my course. But because all we're using is the fact that it's a vector, it really doesn't matter which one we're talking about. And in practical terms, magnetic fields are just a lot easier to measure and control. Here are the materials we're going to be using. This is the magnet. It's made out of a material called ferrite, which I believe is a ceramic of some kind. It's got a hole through the middle, but the hole is really not that important in terms of its magnetic properties. And then we have this magnetic compass, which basically tells you the direction of the magnetic field at a given point in space. And for our purposes, it doesn't really matter that much whether we pay attention to the red needle or the white end of the needle. If you're using these for hiking, it matters because red points north, but we're just going to be measuring how much it twists when we subject it to a combination of two different fields. So it doesn't matter which end we use to measure that twist. Let's first verify that these things actually work. So I have this pair of scissors with a steel blade, and these are not magnetized as far as I know. They were just sitting in my drawer of my desk. If I bring the scissors close to the compass, you can see that they're clearly affecting the compass. That's not because they make their own magnetic field. It's just because the compass needle is a magnet, and so it's attracted to steel just like a fridge magnet is attracted to your fridge, even though the fridge itself is not a magnet. Same thing with checking that this magnet really is a magnet like they claim it is. So it sticks to the scissors. And we can also see that the magnet affects the compass strongly. In order to make any sense out of the results of this experiment, we do need to know a little bit in advance about the magnetic field pattern of this magnet. So here's the actual magnet and then a bigger drawing of it. And those red lines are the magnetic field lines of the magnet. So you can take the vector at any given point in space, which is the magnetic field at that point in space, and then if you chain those together, they make these lines. And for the magnetic field, they happen to close on themselves and form closed loops. They never begin or end at a point the way an electric field would. So what's important for us here is that these disk magnets have a field that has a certain symmetry to it. So for instance, you can see that the right and left are the same. You can also see that the top and bottom are the same except for the direction. If I flip the whole picture over, the arrowheads would be pointing the opposite way. We don't really care that much for the purposes of this lab which way is which, so I'm not even going to bother determining whether this magnet should be flipped that way or that way. That would just cause the compass to deflect in the opposite direction. Because of the symmetry of the field, there are basically two places we can go where we can know the direction of the bar magnet's own field in advance. So there's this plane of symmetry, which is like the equatorial plane of the disk. And at a point in that equatorial plane, that field is guaranteed to be parallel to the axis of the disk, just by symmetry. The other place where we know what's going on is if we go to a place that's on the axis. Then, again by symmetry, the magnetic field is going to be parallel to the axis. So if we're either on axis or in the equatorial plane, we're going to have a field that's parallel to the axis of the magnet because it's been magnetized that way. So starting at this point, I'm just going to go ahead and show you how we would do the actual lab, which is described in the book. This video is not going to explain all of that, so if you haven't read that yet, I would pause the video, if necessary download the PDF file of the book from the website, and read that lab, which is at the end of chapter 1 in the book. So I have my compass and my magnet. First I want to set up the compass by itself, so I'm going to move the magnet really far away. It's a pretty weak magnet, but it can still have an effect if it's too close, so I moved it about 1 meter away. And now it's showing me what direction is magnetic north, supposedly, inside my house. It is true that magnetic north is about that way inside my house, but there's no guarantee of that, and it doesn't really matter that much. There can be building materials that could be creating all kinds of magnetic fields in here, so as long as we have some field in some known direction in this space, we're okay. However, we don't want any interference from any magnetic parts inside the desk. So for that reason, it's nice to kind of get the compass just at least 4 or 5 inches off the desk so it's not going to get interfered with by anything like that. So for that reason, I'm using these paperback books. When we do this lab in the classroom, we're usually taking desks and putting a meter stick between them. And I'm going to put the compass there so it's in the air. Now you get to choose between 2 possible ways of doing this lab, which I'll show you here. One would involve lining things up this way. The other would involve going at 90 degrees. So the idea is that if I set it up this way, I'm first going to line up the ruler so that I can see it's nice and parallel to the magnetic field in this region of space, which is the Earth's field plus whatever I have for my house. And I'm also going to rotate the compass so that the needle is on 0 degrees, which is north on the compass. Get the ruler carefully aligned again. And now in this setup, there's only one axis of symmetry that I can use. I can't do this. If I do something like this, then I'll be measuring the field along the magnet, but that won't work because then the vector coming from the magnet would either be that way or that way, along the same line as the ambient field. But then that won't deflect the magnet very much. And it would only work if I got very, very close, and then I would get some kind of random deflection just because I can't perfectly orient the magnet and perfectly locate the magnet. So with this setup, I actually have to measure this. That means the compass is now in the equatorial plane of the magnet. If you recall that picture of the fountain shape of the magnetic field lines, they go sort of like that. So they would be pointing perpendicular to the ambient field at the location where the compass is. And I think you can see now that I'm getting a small but noticeable deflection of the compass because those two fields are adding like vectors. If I had wanted to measure the field on the axis of the magnet, I would need the magnet over here, but then in order to measure distances, I would need the ruler oriented the other way. So you can choose either way of doing this experiment. Since the magnet has to be tilted up on its side rather than flat, I need to get it up high enough so I can get it at the same height as the magnet. So for that purpose, I just scrounged up this eraser, which I'm going to put right there, and I'm going to carefully locate the center of the compass at 15 centimeters on my ruler so I know where it is. So now if I take my magnet in the correct orientation and bring it closer, you'll see it deflect the compass. It deflects about, probably 70 or 80 degrees yet. I'm not actually taking data right now at this distance. And then if I go farther away, the deflection is smaller. If I get too close, you have to watch out, because when I'm too close, all kinds of random stupid stuff happens. When you're too close, basically just the fact that the magnet is made out of a magnetic material starts to take over. So then you get things like this, just like if I was using the scissors. You don't get real data. So don't get fooled by what happens when you have the magnet very close. You also do have to watch out for friction in these compasses, which are cheap compasses where the needle rubs on the bottom plate because the Earth's field is at an angle like this. So anytime you take data, I would tap the compass a little bit to break static friction and make sure that it settles down in the correct position. So here are some practical things that I had to deal with when I went ahead and tried to take quantitative data here. One issue was that it really started to be a problem that that white tail end of the compass was dragging on that black plate. It meant that even if I tapped it to break static friction, it would still oscillate for a while, but then when it stopped oscillating and stuck, the place where it stuck would be kind of random, and I'd have to try a bunch of times and guess what was the correct place. So what worked well for me there to fix that problem was to tilt the whole setup a little bit. So what's going on here is that the compass is aligning, it wants to align with the Earth's magnetic field, which is not horizontal in most places on Earth. So I took out some books out of that downhill pile there to get that right. Then I had to kind of reinsert something like this pen. And so now what I've accomplished there is that the compass is really freely swinging now and doesn't stick. The other thing to watch out for, I'll demonstrate for you here. If I bring in the compass like this, I think you can see it deflecting the compass needle more and more, and then if I get too close though, I can sometimes get a paradoxical effect where you see how the deflection went back down again? What's happening there is that if I get too close, then it's just like using the scissors. The scissors will just attract either end of the compass because they have no magnetic polarity themselves. So that effect is actually stronger at very short ranges for this magnet as opposed to the effect from the actual field of this magnet. So be aware of that and don't get fooled by what happens when you come into distances that are very short, like 4 or 5 centimeters. Okay, so hopefully that's enough to get you going on this lab at home. If you're one of my students working on this lab and you have any problems, please email me and get in touch. And for the analysis, you should realize that it's important to have the result of homework problem number 2 from the book in order to analyze the data